Okay, so let's go ahead and pick up where we left off. Um, okay, so we're talking about epithelium, and so we talked about the simple epithelium, and now we're going to be talking about stratified, right? So stratified basically is a layering terminology. So essentially, what we have are multiple layers of, in this case, stratified squamous, which would be flat cells, so those flattish pancake-looking cells. One of the things to be aware of, however, is when you have multiple layers of cells, a lot of times the apical surface can look a little bit different than the basal surface. So for instance, if you take a look here, these basal cells right in here, they look more cuboid in nature, as opposed to the apical surface, which look a little bit more stratified in nature, squamous in nature. So whenever you have a stratified layering, you always do your diagnosis of the layering by the apical surface. So the reason why the lower cells kind of look like a different shape is because of the shape distortion associated with the tensions and stresses of all the other layers on top of it. So it kind of distorts the shape a little bit. But typically, you always do your diagnosis with the free surface or the apical surface. And then once you actually diagnose it at the apical surface, then it doesn't change. So once you pick a tissue type, you don't change it in mid drift. Okay, so uh, and that's kind of like a little bit of a tip to basically diagnose what types of tissues you're working with. So that's stratified squamous. Stratified cuboidal is a little bit rarer. However, you essentially have multiple layers of cuboid cells. So in this case, you can see that the first layer down here is the basal layer, and the upper layer is the apical layer. And so oftentimes these are involved in things like secretion, absorption, things like that. So like sweat glands um, and things like that would be stratified cuboid. So you have a couple of layers of cuboid cells. The other one for stratified is columnar. Now this is also rare. You don't really see it a whole lot. So it's basically for protection and oftentimes for secretion. You can see that especially for cuboid and columnar cells, you can see that a lot of their function is associated with secretion. So that is to say the activities of glands, and you tend to see them in glands. For instance, in mammary gland ducts, they tend to be stratified cuboid. Portions of the larynx, some portions of the urethra in males can also be stratified cuboid. Now, the important thing about here is when you take a look at a stratified cuboid, they basically line up in sort of a nice, neat order. So what you can see typically what stands out to you is typically a nice little neat row of nuclei. You usually see those quite clearly. And then you kind of see another layer of nuclei on top of that and another layer on top of that. So basically you kind of see these rows of nuclei. And then that kind of betrays it as basically a stratified columnar. And of course, the columnar cells, if you take a look at the apical surface, are large and rectangular. Typically speaking, a lot of times, sometimes students will kind of make the mistake of misdiagnosing a cuboid versus a columnar. And so the columnars, the important thing are going to be a little bit more rectangular. The cuboids are kind of a little more pudgy, and they're not quite as elongated. The other type of tissue that we have here, and the last one that we have on our list, is the transitional epithelium. Now, remember, transitional epithelium mostly is going to be in the bladder or in the urinary structures, so ureters, urethra, and so forth. And so what these guys do is they stretch. So when they're relaxed, that is to say when the tissue is not stretched, what's going to happen is you'll oftentimes have multiple layers, but on the top, they look kind of more ovoid. Kind of like little ovals. And that's kind of what it looks like when it's relaxed. Then when it's stretched out, what's going to happen is they flatten out. In this case, they start to look more squamous. But a lot of times students will be like, well, how am I supposed to know? Transitional epithelium, typically, it's kind of the giveaway is that typically when you're looking at it like in a relaxed bladder, it doesn't fit the diagnosis that you have for the other tissues, right? So for instance, for cuboid, it doesn't fit cuboid because typically it's not really a cube shaped, kind of more like an oval, like a football. So it looks kind of more like this. So not really flat, so not squamous, and not really cuboid, so not cube, and certainly not rectangular, so not columnar. So it doesn't really seem to fit in any of the shape designations. And so that's oftentimes kind of the betrayal of transitional. If you're trying to get in there, you can't quite get it to fit into all the other ones. And as a result, basically it's transitional because it's a slightly different creature. And it's kind of the outlier, if you will, of all of them. Now, when we take a look at epithelium, right? So this is kind of like a nice little table. You're looking at simple epithelium, and then we're going to be looking at stratified epithelium here in just a second. But for instance, what are some of the things that simple epithelium will do, right? So one of the things that you have for simple epithelium, that is to say single layer, is you're looking for minimum distance for diffusional purposes. So it's oftentimes what you use when you need to diffuse things across short distances from one place to another. For instance, you'll see this lining blood vessels, lymphatic capillaries, the alveoli, the lung are simple epithelium. And so that's basically, that's the simple squamous type of epithelium. You also see simple squamous infiltration, which is kind of like a sieve-like structure. Generally speaking, you see this located in the kidneys. Again, you're trying to basically move fluids over short distances. You don't want a really thick membrane if you're trying to move stuff through it like a sieve-like structure. You want it to be able to go through it and select against size for that. And so that typically you'll see in Bowman's capsules. The other one that you're going to see is secretion absorption, right? So this is a glandular activity. For instance, the mesothelium, which is making different types of fluid in the serous membranes. That's a secretion absorption structure. Also, that's simple squamous, but you also have simple cuboid. For the first time, we're going to see simple cuboid at work in what's called the choroid plexus, which is essentially a structure that's in the ventricles of your brain. And it's a clustering of simple cuboid epithelium along with blood vessels and things like that that will basically make cerebrospinal fluid to circulate through your brain and your spinal cord. It's also in kidney tubules and other types of glands and things like that. Now, the protective role, okay, wow, I really botched that. That's supposed to be a 4 in a circle. So the protective one is something we also see with simple squamous. But remember, for protection against abrasion and friction, basically can't be a lot, right? Because if it were a lot, you would basically have multiple layers, not a simple layer. So where there's just a little bit of abrasion and friction, but it's not a lot of physical torsional strain, we'll see simple squamous liners like in the blood vessels, the mesothelium, which is basically part of your serous membrane system lining your body cavities. For simple cuboid, we'll see this actually in the bronchioles of your lungs. And then we also have a function for the movement of mucus, so ciliated cells. The only one we have here is going to be those pseudostratified ciliated columnar cells that basically line your respiratory tract, make mucus, trap all the dirt particles that you're breathing in, and then it sweeps it out so you can cough it up. And so that's the movement of mucus. And then, of course, we have a miscellaneous group. So, for instance, there's simple squamous epithelium in your tympanic membrane. There's also simple cuboid on the surface of the ovaries. And so there's a couple of different miscellaneous groups. But this is a really nice list, actually. You don't see this in very many textbooks, but this is a really helpful and really nice list. Because to be quite honest with you, the majority of AMP students usually identify epithelial tissue with liners and protection. They oftentimes will completely lose touch with the secretion and absorption and mucus production and things of that nature, which are actually very critical functions and important to understand and to remember. Now let's take a look at the stratified epithelium. Same situation. We're going to look at stratified squamous, cuboid, columnar, and then transitional. So let's start off with our stratified squamous. So first of all, protection against abrasion and friction. So basically lots of stress. Typically, how do you know it's lots of stress? Because you got a lot of layers. So the more layers you have, the more thickness you have, the stronger your resistance to abrasion and friction is going to be. For instance, your skin, the cornea of your eyes, because there is abrasion associated with that, the inside of your mouth, your esophagus, these are all stratified squamous because they are naturally and normally exposed to high levels of abrasion and friction. Now, what about movement of mucus, the ciliated piece? Well, we do see this in the larynx, so that's basically the voice box, where you see your stratified columnar. That's a pseudostratified columnar. It starts in the larynx and moves down into the trachea. There is another one here that we don't have on the other list, which is stretch. So your ability to stretch, that's the one that's going to be typical of transitional epithelium. So ultimately, that one is going to be that's basically going to be associated with transitional epithelium. And so you're going to kind of be essentially like an empty bladder would be a relaxed bladder, and then a full bladder would be a distended or a stretched out bladder. And so that's the urinary. And then of course the miscellaneous stuff for stratified, you have a couple of pieces, right? So for instance, you have parts of the urethra are stratified because of the passage of urine and the abrasion and the friction associated with the passage of urine. Your sebaceous glands, so the sweat glands were stratified cuboid, and the sebaceous glands, which are the oil glands in your skin, are stratified squamous. And of course, you have your sweat glands, your salivary glands, and ovarian follicular cells. These are all stratified cuboid in nature. The stratified columnar, you're going to see that in the urethra, in the male urethra, the epididymis, the ductus deferens, and the mammary ducts in females. So large portions of the tubular system of the male reproductive system and in the mammary system in females. So you can see this is a really nice spread because it basically puts all the major different types of epithelial tissue, and it kind of nicely, neatly arranges them and organizes them into a nice little functional chart. So when you're studying for this chapter, that's a really good set of tables to work from to make sure that you understand everything in terms of the function of what these things are doing. So now let's take a look at the free surfaces of the epithelium, in particular, the modifications associated with them. So what you're doing with the surface modification is you want to increase your surface area so that you can increase your productivity. You want to be able to do more without paying for more. And so ultimately, if you have the surface of your epithelium and it's smooth, then usually what you're trying to do is you're trying to reduce friction. That basically is less contact equals less friction. And so oftentimes when we have something like that, we refer to it as endothelium, inside layer. That's basically what it means. Now, oftentimes what will happen is the inner surface will be folded up. So for instance, transitional epithelium will be folded up so that it can spread out. So basically the folds allow for expansion. Kind of like something that's unraveled, and then you kind of put tension on it and it sort of allows you to sort of spread it out. You will also see on free surfaces something called microvilli. What this does is basically increase the surface area for absorption secretion, typically in the columnar cells associated with the digestive tract. So essentially on your columnar cells, what will happen is you'll have these little hair-like structures to basically further increase your surface where you can absorb material. And so these basically are the columnar cells that are associated with the absorption of your nutrients in your intestines. And so you'll kind of see this like little, looks like a little eyeliner histologically, a little layer on the top, and that's basically going to be the microvilli designed to absorb things. There are some special microvilli called stereocilia, and so these you'll find in the inner ear. They're technically not cilia, they're actually microvilli, but these basically act as sensory receptors and basically are part of the mechanism of hearing. And how you hear things. And then, of course, we have the cilia proper, which basically moves mucus across cell surfaces. Okay, so these are the different modifications that you can do to the free side of the epithelial layer. So it's not all just smooth. Now, another piece that we're going to be taking a look at is glands, right? So that's we talked a little bit about the liner abilities of these epithelial cells, of these epithelial tissues, and now we're going to talk about the secretory capacity of these epithelial cells. So we're going to look at secreting organs. Now, when you take a look at a gland, there's really two types of glands. There's what's called an endocrine gland, and an endocrine gland basically is any gland that will basically take its secretions and it'll dump it into the blood vessels, right? So basically dumps the secretions into the blood vessels, directly into a blood vessel. An exocrine gland typically is where the glandular secretions are loaded into a duct. And so typically you'll have a ducting system that will receive the secretions, and then from there the ducts will deliver the secretions to wherever they need to go. Now, when you take it's kind of like a tunnel system or a channel system, these duct systems. And so the exocrine glands, because they have a ducted system, you can have different structures and different shapes of these ducts themselves. So you can classify an exocrine gland by the structure of the duct that it uses. And so this is kind of what it looks like. So this is the most basic of all the secreting cells, right? It's called the unicellular gland. So basically a single cell, like a goblet cell, for instance, it's secreting mucus. So that would be considered a unicellular gland. So one cell, no structure, no duct. It just basically spits its secretion, in this case, the mucus, outside of itself to create a little mucus layer on top here. Now, if you start to create ducts and you're basically having your secreting cells dump them not just randomly outside, but you're actually having them put them into the duct themselves, then you can start organizing the structure of your ducts. For instance, here you can see what is called the simple tubular gland. So for instance, your gastric pits in your stomach are organized this way. But basically your secreting cells will dump the secretions into the lumen of this duct. The term lumen just simply means the inside. And so what will happen is you'll fill this duct up with secretions, and then you can deliver it through the ducting system from there. You can also elaborate this a little bit more by creating multiple pockets within one duct. Now, a simple tubular duct is simply an invagination. That's basically kind of a pucker inward that just essentially kind of takes your cellular layer and just basically dips it down into the connective tissue structure, creating almost what looks like a little shaft, like a little mine shaft. Okay. And so that would be an invagination. Now, a simple branched tubular would basically be a situation where you have tubes. So you have these kind of tubular structured, I guess, leaflets, if you will, that are still tubes, right? So they're still shaped like tubes, but you have more of them. So branches off of the main tube, and that's a simple branched tubular. And so typically we'll see this in like the lower portion of the stomach, the pyloric region of the stomach. And then what we can also have is a slightly different shape. So for instance, when we invaginate, we don't necessarily have to have tubular in shape, but we can have what's called acinar in shape. So basically an acinar situation is where you have this like little poofed out pouch at the end of a long channel, in which case basically you secrete your secretions into this like little structure, this little pouch-like area, and then it'll basically be delivered through the duct system. So that's called a simple acinar. Your sebaceous gland, your oil glands in your skin are organized this way. And then if we want to make that more complicated, we can generate simple branched acinar. That basically means it's still simple, single layer, it's branched, and it's acinar, so it's pouch-like. So in this case, you do the same thing, only instead of being tubes, you have these little pockets or these little pouches on each end. So that's going to be the acinar, branched acinar types. Okay. So this is kind of like what the sebaceous glands are like. They're kind of like these multiple systems of branched and pocketed or acinar types of glands. We can keep going. So those are the simple glands. And so ultimately, when you take a look at simple, they're to be compared to compound glands. This is basically where you have tubes on the tubes, so branches on the branches, right? That's what we mean by compound glands, so that the branches have branches. So let's take a look at it. So basically, first of all, you see your main duct here, up here at the top, and then it branches into three major conduits, which themselves are branched into multiple conduits. So each branch will branch. So here's a branch, and then it'll branch out into a second layer of branches. That's why it's called compound, because the duct will separate out into three branches, just like we had before with the simple tubular. But then what'll happen is those tubes will then branch themselves. So they'll branch a second time, like sub-branches. And so this is what's called compound tubular, because the shape of the terminal structure is a tube. It's a glandular tube. So your mucus glands in the duodenum are similar to the structure. We then have compound acinar. We have the same basic idea, only in this case, you have the pouch-like termination. So here you have your main duct, and then your duct is going to branch. So that's your first level of branching. So here's the first one. And then those branches are going to branch again. So this is the second, what I'm going to call the secondary branching. So it goes straight, and then that branch will branch, and then this third branch will branch. So you can see it's a branch of branches. And the terminal structure of that is the little pouch-like structure. So that's going to be the acinar structure. Then you can have a mixture of them. You can have compound tubular acinar. This is what happens in pancreas. So for instance, here's your compound, because you have your duct up here, and then that branches into 1, 2, and 3. And then each of these branches will branch off into 1, 2, and 3. So this one is all acinar. They're little pouches. This one will branch into a combination. So here is a little bit of an acinar. This one is a little bit more tubular. And this one is a little more tubular. And this one will branch into 2, one of which looks pretty acinar. This one maybe is kind of on the line. It could be a little tubular and a little acinar. So basically, when you're branching off, you don't have to be all acinar. You don't have to be all tubular. You can mix and match them, so you can have these branches be partly acinar and partly tubular. And so that would be a compound tubular acinar gland. Okay. Wow, everything you guys wanted to know about glands and then some. But we're still going. So more about glands. So there's 3 different types of glands, of exocrine glands, and they're kind of important. They're basically classified by how they excrete. Not by their structure, but how they secrete. Okay. So the first one is what's called merocrine. Now, merocrine is basically a situation where the cell uses exocytosis to liberate its secretion. And so this is kind of what it looks like. So here you can see the cells are just naturally going through secretion. So they're little secreted, their secretory vesicles are fusing with the membrane, and it dumps their contents to the outside into the duct itself. Now, the good thing about this is basically normal transport. You may remember this from 1080, right? This is the secretory pathway. It's an absolutely normal thing for a cell to do, to basically make a secretion to communicate with the outside world. And then it bundles that up into a secretory vesicle that fuses with the membrane, and then that dumps the contents to the outside world, in this case, into the duct itself. So this is normal transport. The cell's quite happy. Then we have what's called apocrine. Now, apocrine is a little bit different. Apocrine is basically when you pinch off fragments of the cells themselves. And so this is kind of what it looks like. So here's your apocrine. So you can see how basically you get these little fragments that are essentially full of your secretion, your protein or whatever it is. And you pinch off little bits of it and you basically dump that into the duct. And then all that secretion gets liberated into the duct, and then it gets moved out of the duct system to wherever it needs to go. Generally speaking, this is a little bit different, a little harsher, right? Because you're basically pinching stuff off the cells, and so that could be a little damaging to the cell. But still, you get the job done. And the last one is called holocrine. The holocrine basically is where you have a shedding of the entire cell. For instance, the entire cell blows up. And as it blows up, it releases its secretion. Think of it as sort of like a little a secretion bomb, right? So basically it blows up, and then it's like a water balloon. You basically just blow up and you just release all of your secretion to the outside world. So this is what's happening here. So here you can see in the duct, entire cells which are popping like water balloons, liberating all of their secretion into the duct, and then the secretion that you're secreting will then be delivered to wherever it needs to go. So the way to remember holocrine is, I always remember it as holocrine is Holocaust, right? So it's kind of like similar in nature. So you have Holocaust, which is basically, you can either think of one of two ways. You can think of the historical Holocaust that happened in the 1930s and 40s, which is horrible and a lot of death and destruction, which is exactly what happens with this guy. Or you can think of Holocaust as a fire, which is also a lot of death and destruction if you're in the middle of a Holocaust, a fire type of a Holocaust. Either way, it's a lot of death and destruction, which is exactly what happens to the cells. A lot of death and destruction. The cells blow up and die, and then they release their secretions into the actual duct so it can be delivered. So those are your main ones. So a good example of that is like your sebaceous gland, your oil glands. So that's what they do. They basically self-destruct, and then they dump the sebaceous oils into the duct for you to deliver to your skin. Okay. So here's kind of a little bit of a rundown, a little bit of a visual rundown. So you have pseudostratified ciliated epithelium, columnar epithelium. You can see the goblet cells in there. That's basically the goblet cells that you see here. And then you can see the cilia, that little border right there. That's the cilia that are essentially kind of pushing the mucus up into your respiratory tract. So you'll see that in the trachea. Then you have your simple columnar epithelium, which you see in your digestive system. So that's this guy right here. So you'll see that in your intestines. And then you see simple cuboid here in the tubular system of your kidneys. And so that's basically coming from your kidneys as well. And also, in this case, your simple squamous epithelium. Remember we talked about that as those really, really thin layers of epithelium that are lining the surface of this little capsular space. So that's going to be simple squamous. And so that's also going to be in the kidneys themselves. Your transitional epithelium, which is stratified, is going to be found in the bladder for the most part. So that's going to be your transitional, and then your stratified squamous or flat is going to be, okay. Hold on, let me see here. I believe, got a good old fashioned, I guess that was a PowerPoint crash that time. Can't get through, cannot get through a class without something crashing on me. I guess it's welcome to the 21st century. Okay, then we have transitional epithelium, and then we have stratified squamous, which is basically going to be in the skin itself. Okay, so that's kind of just a general, basic, simple rundown. That's pretty simple, pretty basic, but that gives you a good idea of sort of the epithelial group. It's a pretty big group, a lot going on there, a lot of important physiology happening in epithelial tissue. Okay, one down. Now let's go ahead and move into connective tissue. This is another really big tissue region, is connective tissue. Matter of fact, between epithelial and connective tissue, that usually takes up like the lion's share of the tissues chapter. So connective tissue is pretty much everywhere. We've already seen it actually, just talking about epithelial tissue, but the construction of connective tissue is not cellular. The connective tissue is governed by extracellular matrix. So essentially, the extracellular matrix that the connective tissue cells secrete becomes the actual tissue that we usually think of in terms of supporting other tissue types. And so there's a lot of different types of connective tissue. And you can imagine that because connective tissue is a general supportive type of a tissue, that you have a lot of different types because you have a lot of different applications for support, right? So sometimes you need a little bit of a support tissue, like a foundational tissue to anchor yourself onto, but because it's going to have a lot of physical torsion and strain, you need a lot of structural power to it. In some cases, you're not going to have a lot of physical strain and stress, and so you still need connective tissue support, but you don't need quite as much structural integrity associated with it because you're not going to be buffeted around and beaten around by like things like abrasion and things of that nature. So there's different types of connective tissue for a whole host of different ranges and functionalities that your tissues ultimately need. So when you take a look at connective tissue, the functions that we run into, there's actually quite a few. And so probably more than people are aware of, and that's typical. First of all, they're designed to enclose organs, right, and basically divide them into layers. So it's a kind of a structural, organizational type of a thing. They're also the connectors. So to connect one tissue to another, for instance, tendons connecting muscles to bones and ligaments connecting bones to bones. So these would be connectors connecting one type of tissue to another type of tissue. And they're also there for support, structural support, and also for movement, ambulation. So bones, for instance, is a good example. It's a type of connective tissue. Connective tissue is also responsible for fat storage. So you can store fat in your connective tissues, like for instance, adipose tissue, which is fat cells. It can be used to cushion and insulate. For instance, that's one of the roles of fat. So to insulate you from weather, and also to cushion or to provide a kind of a pad, if you will, especially for your organs. It will be involved in transport. For instance, blood is a type of connective tissue that transports oxygen throughout your body. And it's also a protection for you. For instance, the immune cells, the cells of your immune system, are born and carried around in a type of connective tissue, lymph. And so when we take a look at connective tissue, it has a whole host of different functions, and they're all very, very important. So connective tissue, you could think of, is kind of like the main attendant, if you will, of all the other tissues. So if you think of somebody famous or somebody popular, oftentimes they kind of have an attendant, right? Somebody who kind of manages their sort of day-to-day activities, who manages their schedule, who takes all the calls or whatever. The president is this way. He usually has some sort of an advisor that's always with them, chief of staff perhaps at times, but there's always some person. It changes from president to president. There's always one person or maybe a couple, and they are like the ultimate supportive role. They're always there to give advice, to run down policy consequences, and to kind of help the president sort of strategize and to sort of problem solve. And so this person represents a sort of a background supportive role, and they're always there functioning to support all the activities that the president's doing. And so connective tissue is the same way. Connective tissue is always there. It's everywhere as a support and as an attendant or an advisor, if you will, of all the other tissues. So how do we make connective tissue? First of all, we need cells to secrete extracellular matrix, which will actually become the tissue itself. And so we have those cells. So our specialized cells come in 3 flavors, and this is pretty typical for all the cells that we see in connective tissue. The first thing we run into are what's called blast cells. So these ones are the cells that lay down new matrix. Oftentimes in development. So like, for instance, if you were taking developmental, like embryology or something like that, developmental biology, and you're studying embryology, you'll see blast cells everywhere because you have new cells, brand new cells, and that are laying down new structure. And they're considered blast cells. So these are laying down new matrix. Then blast cells will either give way to or they will mature into sites, which basically are mature cells that maintain the matrix. And simply they'll do repair and replacement of existing matrix. And then typically you have what's called classed cells. So classed cells is a group of cells that breaks down the matrix for typically remodeling purpose. So you can build the matrix and you can break it all down. And that's pretty typical of connective tissue. For instance, connective tissue cells that basically make the framework will be bone cells. There's bone cells, for instance, there's osteoblasts, which form the bone. So they basically lay down new bone matrix called osteoid. And then they mature into what's called osteocytes that maintains your current bone and replaces the worn out bone. And then you have osteoclasts, which will break your bone down. Now, you also have cartilage cells. So the cartilage cells are what's called chondrocytes. So cartilage is the root for cartilage. And so the chondroblasts are the ones that basically form new cartilaginous matrix. And then eventually they will grow up into chondrocytes or cartilage cells that will then maintain your cartilage and repair and replace. And then you have fibrous tissue, which will be fibroblasts, which are a special type of a blast cell that will form fibrous connective tissue. And typically this will lay down new connective tissue. And they'll mature typically into fibrocytes, which will then maintain that connective tissue. So you can see a pattern, right? The blast cells will lay down the new matrix. They'll secrete the extracellular matrix, and that will become the tissue of the connective tissue that we know. And then they will graduate, or they will mature into the sites, chondrocyte, astrocyte, fibrocyte, and then those will maintain the existing matrix that has been laid down. And if it gets damaged, they will replace it. And if it needs repair, they will repair it. So that's kind of basically what we have. So now let's take a look at some of the other cells that we see in the connective tissue. So those are the three main ones: the blast cells, the site cells, and the clast cells. Now let's take a look and see some of the specialized cells. So first of all, one of the ones that we'll see in addition to the big three are fat cells, adipocytes. These basically are common in lots of different tissues, the dermis, for instance. It's rare in cartilage, but you will see it in the dermis. And these basically are holding fat inside them. And fat has several different roles that it plays. This is the reason why it's in a lot of tissues. But we'll get to that once we get to the fat cell section, the adipose section. You also have what's called mast cells. Generally speaking, you see lots of mast cells hanging out underneath membranes, like, for instance, the serous membrane. So blood vessels and things like that. So oftentimes the mast cells will be important in inflammation. So they'll release heparin and histamine, which are basically dilators. They're vessel dilators and also blood thinners to basically improve or to speed up blood delivery to a particular site of inflammation or site of injury. They will also marshal proteolytic enzymes. So these are basically enzymes that are basically protein cutters. Right, so they basically cut proteins, and so that's all in response to injury. So mast cells are involved in inflammation response. And typically you'll talk more about inflammation response and wound healing and that sort of stuff when you get into AMP2. You also have white blood cells, which are there. So these are obviously the parts of your immune system that are responding to injury or infection. You have macrophages, which are also immune cells. So they'll do phagocytosis. This is where this is cell eating. This is when a cell gobbles up another one. So that'll gobble up bacteria to protect you from foreign invasion. So you have two different types of macrophages. You have one group that's fixed or outposted in a particular place in the connective tissue. So it's like a garrison or a substation, where you hang out, and that's kind of where you serve. You also have the wanderers, right? These are the patrollers. So the macrophages will basically move by amoeboid movement, which is kind of like oozing, like a blob. And they'll move through connective tissue, and they'll kind of like patrol the body through the connective tissue. And so those are very important cells. You'll talk more about those as well in AMP2. And then you have platelets, which are basically fragments or chunks of a homeopoietic cell called a megakaryocyte. So this is involved in your blood clotting. And so these are also part of your connective tissue. You'll see these in the connective tissue because they have to be everywhere in order to get that blood clotted. And then the other thing that you'll also see, which is important, are a type of stem cell called mesenchyme cells, or undifferentiated mesenchyme cells. And so what these guys have the ability to do is to essentially convert or become any other adult cell type. So when you take a look at a stem cell, what a stem cell does, its job is to basically go through cell division, because your stem cell is essentially the source of new cells. So whenever you have to do and make new cells, and you have to replace old cells that are getting worn out, you have to have a stem cell to do that. So basically stem cells are the source of all new cells in the body. So for instance, your skin, which you're constantly sloughing off and constantly replacing, has to have a source of stem cells to keep adding new cells to that constant rotation. And so what a stem cell basically does is it'll go through mitosis, and when it goes through mitosis, it's going to create two identical cells. It replaces itself with one of those, so that becomes a new stem cell, and this one will differentiate into a terminal cell, some sort of a specific cell that you happen to need. Okay, so for the reason, and the one that you actually went through all of this for. So those are some of the other cells that you see in connective tissue. So first of all, let's kind of take a pause and just sort of think about a little bit more globally what we've kind of gone through. The fact that connective tissue is largely identified by the secretions of the connective tissue cells themselves. That is to say that connective tissue is dominated by extracellular matrix. Not only that, but connective tissue is a very complex amalgam and a gamish of both extracellular matrix and also other supporting cells that have different jobs and functions within the connective tissue itself. So you can imagine then that the tissue that these connective tissue cells lay down becomes kind of the structure or the base or the foundation for the activities of all of these other cells and all these other complex and diverse functions. So basically we see a picture then of a connective tissue that's not just about support, but it's also about all these different sorts of activities, lots of functions and lots of complexity to it. So it's a multifaceted type of a tissue. So then, just wanted to paint that picture before we started moving into the idea of extracellular matrix, because the extracellular matrix is essentially the major component of connective tissue. And the extracellular matrix itself has three major pieces to it, right? The first one is typically there's a protein component to your extracellular matrix of one stripe or another. And the cell, depending on what it does, has the liberty to choose what types of protein fibers to put into its matrix. However, the protein fibers just don't go out there. You have to put them in some sort of a background substrate. And we call this background substrate ground substance. Ground substance is kind of like a gel-like substance that's typically full of polysaccharides and proteins. Oftentimes it is lubricating, and it can differ in consistency. So you can have a ground substance that's very thick and viscous, almost gel-like, so it's a very stable, hard sort of a thing. Or you can have it to be very fluid and runny. So you can have a lot of different flexibility in how you build your ground substance. And then, of course, you have varying amounts of fluid. That's the last piece that is in the extracellular matrix as well. And of course, this fluid will increase the fluidity or the viscosity of the extracellular matrix. And so you have a lot of variation and a lot of play there. So just with that, you can actually build a lot of different types of extracellular matrix that have a lot of different types of functions. So let's go ahead and take, first of all, a look at the protein fibers. So the protein fibers that you're going to see dominantly in the extracellular matrix in connective tissue is, first of all, collagen. That's going to be the biggie, probably the most common. It's going to be very strong and tough. So this is a structural sort of a thing. It'll be flexible, but it's inelastic. So basically, it doesn't stretch. So this is not going to be what you want if you want to get a little stretch going on, okay? So we'll have flexibility, but the flexibility is going to be different in terms of the direction and the planes of tension that it can adopt. So it can only stretch in like one main direction. You then have also what's called reticular fibers. So these typically will be very, very fine, thin, collagenous types of networks. So a collagen is going to be typically a very thick kind of a protein cable. The reticular fibers will generally be much finer collagen fibers, and oftentimes they'll be branched. And so these are used typically to fill in the spaces between tissues and organs. What that basically means is this is used as loose fill to fill in dead space. So notice one of the things that you don't want when you're building a tissue is you don't want to have air pockets in your tissue, because that's a bad thing, because that'll basically create bubbles. And if you have air pockets in your tissues, then you're going to be subject to all of the pressures associated with gases. And it'd be kind of like you can imagine yourself getting sort of a mild version of the bends if you have different types of pressures happening and you have air trapped inside your tissues. It would actually be quite debilitating for your tissues, and it could actually harm the function of your tissues, make it difficult if you have a gas pocket in in the middle of your tissues that's starting to expand because you're at altitude or something of that nature, or you're going, diving or something of that nature. So that would make it very difficult and very tough on your tissues. So instead of having air pockets, you typically will fill in all those air pockets with some type of loose fill. Now, if you're an organ, and typically it's reserved for mostly organs, you'll see the reticular tissue basically filling in those air pockets to give you a little bit of tough filler. And so it's a collagenous type of filler. And so generally speaking, it creates kind of these little nooks and crannies. It almost looks like little cubicles a lot of times. And so within that, you'll see, different cells and things like that in there that'll be inhabiting that. So you see this a lot in the spleen. So the spleen has a lot of reticular fibers in it. Kind of creates like this little cubicle looking structure to give the spleen structure, because otherwise, if the spleen didn't have that, the tissue, which is all cellular, would essentially just be like applesauce. So the spleen wouldn't actually have a structural rigid shape to the organ. It would just be like a pile of mush, like a pile of applesauce. The other major protein fiber that we see out there is elastin. Not elastic, elastin is elastic. But basically, this is retractile, just like a flexible elastic rubber band. So it'll stretch, and then it'll also recoil, basically return to its original shape, and then you'll be able to stretch it out again. So just like an elastic band, okay? And so that gives you more flexibility and more stretch in your connective tissue. Very important for those connective tissue regions where you have a lot of high mobility or a lot of high movement in that particular region, and you need to be able to stretch and bend and move along with the object. Like, for instance, your hand, your skin is notorious for having elastin in it. It's got to have that elastic recoil in there, because as we move our body, our skin has to be able to stretch as we're moving our arm, and then it has to be able to recoil. So it's like spandex. Our skin is like natural spandex. Okay. Now let's take a look at the next one. So we're working our way through our list, right? We started off with protein fibers. Now we're going to go with ground substance. So ground substance basically are essentially the backdrop, if you will. And what you see in ground substance, there's a couple of things you see in there. One of the big ones you see is what's called hyaluronic acid. Now, some of you guys may hear some of these. They may be familiar to you because you may actually run across these in like the cosmetics aisle and things like that. But hyaluronic acid is a polysaccharide. It's slippery, so it's a good lubricant. And actually, we see a lot of hyaluronic acid in the vitreous humor of the eye. So this is basically the fluid in the eyeball. So behind your lens, that jelly-like vitreous is a lot of hyaluronic acid. So it's very slippery, and it's a good lubricant. The other one we're going to see is a lot of proteoglycans. So these are basically protein polysaccharide sort of fusion molecules, like glycosaminoglycan, which is the amino part is a protein, glycan is the carbohydrate piece. And so this is basically where the protein part will actually attach the hyaluronic acid And what it does, it traps water. So basically what's happening is it kind of creates this almost like net-like structure as it cross-links with the hyaluronic acid, and it basically creates a trap. So it's like a net to trap water. And so that's ideally is supposed to, give your skin good hydration, keep your skin good and hydrated, because, well, we all know what happens when our skin starts to dry out. It starts to get very dry and cracky, and then it'll start splitting, and then we'll start bleeding all over the place. Like you got into a good bar fight, our knuckles will be all split open and things like that. And so the proteoglycans and the hyaluronic acid works together to trap water and moisture. And then you have adhesive molecules. Typically, once you have these things cross-linked to hyaluronic acid, the proteoglycans will be held together by these adhesive molecules, and ultimately it kind of binds everything together. So chondronectin is the adhesive molecule that you'll see in cartilage. Osteonectin is what you would see in bone. And then fibronectin is what you would see in fibrous connective tissue. And if you take 1080, you may remember fibronectin as the protein that anchored cells to its extracellular matrix. So this is a type of adhesive molecule that has the effect of binding all these proteoglycan hyaluronic aggregations together, so that you can have a nice, good, stable sort of a matrix, kind of a structural scaffold, upon which then you can overlay your protein fibers. And so if you want a little bit more lubrication, you can add a little more hyaluronic acid to it to kind of slippery it up a bit. So here's kind of what it looks like. So here's your collagen fibers, those tough collagenous cables. And then your elastic fibers, which are typically are kind of cross-linked to each other. Usually they'll kind of look like this. It looks kind of like some sort of an art rendition. So this is recoiled elastin, so it's relaxed. It's not stretched. And then when it gets stretched, it's basically going to pull tight, and you're going to see these cross links kind of pull into nice parallel sections. So this is your stretched elastin. And then when you relax it, it goes right back to that recoiled look. So it kind of goes back and forth and back and forth. And that's what gives your tissues elasticity, if you need elasticity. And then the proteoglycan aggregates, basically, this is what they look like. So let's see if I can blow this up a little bit. So here you have basically your hyaluronic acid is going to be this piece right here. So you can see there's your hyaluronic acid basically running down the center of this entire molecule. And then the proteoglycan monomer, that is the protein carbohydrate structure. So that's what these guys are right here. So this is one big proteoglycan monomer that's made out of protein and the carbohydrate. And so those are typically tethered to and cross-linked to the hyaluronic acid, creating this gigantic, almost fan-like net, so that water gets trapped in this structure, almost kind of like a sponge a little bit, kind of trapping water in the structure. And so that allows you to be able to increase the water content and the fluidity of your tissues so that they don't dry out and become a problem. Okay, so now let's go ahead and take a look at the classification. But before I get to classification, how's everybody doing? Is everything making sense? You're kind of still with me? Still alive?
Yep, still with you.
Good. Good, good, good. Okay. So, so here's how we classify things. First of all, let's get the embryonic stuff out of the way because we did that also for the epithelial tissues. And so the first thing for embryonic connective tissue, we start off with the mesenchyme. And remember, those mesenchymal stem cells were the ones that were responsible for differentiating into all other cells. And so that's kind of what's happening during the embryonic phase. We also have mucous connective tissue a lot in the embryonic stage as well. And so that's kind of a big chunk. So we have embryonic connective tissue. And so we don't have a lot of it when we're adults, but we do have a little bit of it. And so it's a holdover from embryology. The adult connective tissues, however, come in a lot of different varieties. First of all, we can break these guys into what we refer to as connective tissue proper. And then we have supporting connective tissue, and then we have fluid connective tissue. So when we take a look at connective tissue proper, we can further subdivide this into what's called loose connective tissue and also dense connective tissue. Now, if you look at other books or other sources, there's other ways to organize this as well. Some will refer to fibrous connective tissue or loose connective tissue or things like that. And so there's different ways to look at it. But I like the way Seeley does it in terms of loose and dense. Typically in loose connective tissue, you have fewer protein fibers, you have a lot of ground substance in there. And oftentimes your loose connective tissue will oftentimes be used for loose filler in areas without lots of physical and mechanical stress. So if you have a tissue and you have an airspace and you need to fill it with some filler, but you're not going to have a lot of tough mechanical stresses on it, so you don't need a lot of structural integrity, you don't need a lot of structural strength in it, then you can just fill it with some sort of a loose connective tissue. Then we have dense connective tissue. Dense connective tissue is going to have more protein fibers, it's going to have less ground substance in it. And we typically can subdivide this into two different types. We have dense regular and dense irregular. And so basically they're both either collagenous or they are elastic. So we have dense regular collagenous, dense irregular collagenous, dense regular elastic, and dense regular or dense irregular elastic. Okay, so hopefully you followed all that. But this is in dense, oftentimes we'll use it depending on what it's for, but sometimes it'll be either used for connection or for loose fill with more structural integrity. And we'll take a look at that here in just a second. The supporting connective tissue basically is cartilage, which is composed of a semi-solid matrix. So your cartilage is very typically, not always, but somewhat flexible relative to bone, for instance. And you have three different types. So you have what's called hyaline cartilage, which is probably the most common, fiber cartilage, which is the least common, and then you have elastic cartilage, not to be confused with elastic, dense elastic connective tissue proper. So it's oftentimes a common mistake that students will intermix those two because they're both elastic, but they're not both the same. So it's a little bit different, and you use it a little bit differently than the dense elastic tissue. Then the supporting family, you also have bone, which is a solid matrix, unlike cartilage. And you have two different versions of this. So you have what's called spongy bone, and you have compact bone. And we'll take a look at the structure of both of those. And then the last of the fluids, or the last of the connective tissues, are the fluids. So of which you have blood, and then hematopoietic tissue. So either red or yellow bone marrow, and so forth. Another type of fluid connective tissue would also be lymph as well, but that's only isolated to the lymph system. So oftentimes we don't talk about it. So let's take a look at the embryological. We'll basically go down our list, just like we did with the epithelial structure, and we'll just kind of start knocking them out one by one. So basically, when you take a look at the mesenchyme, so this is going to be the foundation. So this is like the common ancestor or the parent cell or the parent tissue. And from this, you get all of your connective tissues. And so as we basically grow up, the mesenchyme cells will basically divide and differentiate into all the other connective tissues. And then we have an outpost of mesenchymal cells that stick around so that we can generate more tissues from that, right? We talked about those already. Those mesenchymal stem cells, those are basically embryological holdovers that will essentially hang out so that we can replace cells with them. So we'll just hang on to a small group of them and we'll use them to repopulate our connective tissue cells. Our mucous connective tissue. So this is the stuff that basically doesn't become specialized. And so typically we'll see this in the umbilical cord of the newborn. But basically it's typically will have reticular fibers in it and things of that nature. So the structure of the umbilical cord is actually coming from this mucous connective tissue. Okay. Now let's take a look at the main adult divisions. First of all, starting with connective tissue proper. So the first of the connective tissue proper is the loose type of connective tissue. So we're going to be talking first of all about the loose. The first one on our list is areolar tissue. Now, areolar tissue, this stuff is loose fill. We said this is loose filler. And so oftentimes you'll see that there is typically a series of all sorts of stuff in there. There's a very, very complex network of, you'll have collagen in there, you'll have elastic fibers in there, you'll have macrophages in there, you'll have lymphocytes in there, you'll have fibroblasts in there. So there's a lot of things in there, but remember the function is for loose packing and basic support for overlying epithelial tissue. So here you can see you've got basically this sort of loose connective tissue that's typically underlying a lot of times the epithelial layers of the skin itself. Okay, so ultimately you'll see this throughout the body. Very common. It's right underneath the epithelial basement membrane, and it'll just be like loose packing. But remember, there's another loose filler. This one is for areas that don't have a lot of mechanical stress. There's another type of filler that you can use if you're in an area where you have a lot of mechanical stress. But for the most part, you're just basically just underneath the basement membrane, and it's basically what your basement membrane is resting on. So light packing, for instance, just packing in the spaces between glands, not a lot of physical strain there, right? Some of the places in between muscles and nerves, just sort of filling in the gaps and the nooks and the crannies and things of that nature. So that's what areolar is used for. Another type of loose, we're still in the loose territory, is going to be adipose tissue. And so ultimately, this adipose tissue, which is white at birth, turns yellow as we get older. And so it has fat in it. So a droplet of fat or lipid is inside the adipose cells. So these are basically the fat cells. And so we also have not just white fat or yellow fat, but we also have what's called brown fat. And so this is basically fat droplets that gets colored by what's called cytochromes, which cyto means cell, chrome means color. So they're color cells, essentially what it is. and they're specialized to generate heat. So that's like your insulation. And this is kind of what they look like. They basically look like a gigantic white cell, and that little droplet inside there is fat. So you got a droplet of fat in there. And so you'll see this everywhere. So this is loose packing. This is a packing material. So it's got a lot of stuff associated with it. Not just does it pack those empty spaces, fills in those empty spaces, but because of the brown fat, you can also have thermal insulation just underneath your skin, for instance. Fat is a highly energetic molecule, so you can have energy storage. It's also capable of protecting your organs. It's like putting a pad on your organs to protect them against injury and things of that nature. So you'll see fat tissue everywhere in the body, especially just underneath the skin. And then the last one is reticular tissue, or this is our fine network of reticular fibers, those collagenous fibers that are kind of irregularly arranged. And so what they do is they create these sort of nooks and crannies. It's almost like they create cubicles to give an amorphous organ structure. So lymph nodes and spleen are a good example. This is a shot of a spleen. So notice what you see here. What you see is mostly cells. So these are leukocytes or white blood cells in the spleen itself. And so what you see is mostly cells, but those black ribs, those actually form like little false walls, like the walls of a cubicle. They basically create these little nooks and crannies and a little bit of structure for the organ, so that the spleen has a little bit more rigid structure within which then these cells can inhabit and they can do their work. So if you didn't have these, then the spleen would just be a pile of mush. And so that's kind of what reticular fibers are for. They're typically associated mostly with giving a little bit of structural shape to organs itself, but they are a type of loose, also connective tissue, but they basically give shape and structure to organs. Okay, so those are the loose. Now let's go ahead and take a look at the dense. So the dense is basically going to be typified by having lots more fibers in it. And so you have a couple of different types, and I'm going to sketch these out a little bit. There's a little bit to go through here for the dense types of connective tissues. So this is the last half of connective tissue proper. But first of all, the first one that you're going to have is what's called the dense regular collagenous connective tissue. Generally speaking, this is going to be composed of collagen fibers, lots of collagen fibers that basically fill and are dense. So there's like a dense collection of collagenous fibers. And so you can see these this collagen. So each of these little individual nuclei are the cells, the fibroblasts, but all this material here, this light waves of pink material, that's all collagen. It's just basically laid down in waves. So here's your cell here, but all this right in here, these are just all wall-to-wall collagen waves that are laid down. And so typically these will create a lot of good structure, right? So basically, number one is they're tough. So they will withstand pulling forces, like for instance, what you exert when you pick something up. They also have a little bit of stretch resistance, so they're not going to stretch out. And they've got what's called tensile strength. So tensile strength is basically your ability. What tensile strength is actually a metallurgy term. If you take a metal bar and you pull it on this end and you pull it on this end, the amount of tension required to make this thing sort of do a taffy pull and break apart is its tensile strength. So your ability to withstand that opposing force like that, to be basically drawn and quartered, pulled apart, by the proverbial horses, that's your tensile strength. So you can pull on your collagenous fibers and still be able to withstand that tension. So one of the reasons why this is the main type of connective tissue when you take a look at tendons and ligaments, both of them are basically very high tension environments, like your muscles, to withstand force, the forces that you exert on your muscles and on your skeleton. So that's your dense regular. It's laid down in nice smooth waves of collagen. And some of you may have seen this in the histology lab. So it is past our witching hour. So what I want to do is I want to start here with the dense irregular. And then we'll take a closer look at that one because I want to compare that one to a couple of the loose ones just so we can tease that apart. But we'll start with that one and finish up the connective tissue proper section and then move through the rest of them.